Hi everyone. Today, we're diving into the future of the semiconductor industry. We'll be discussing the end of Moore's law and the breakthrough technologies waiting on the other side. For decades, the semiconductor world lived by a simple rule of thumb, Moore's law. It predicted that the density of transistors on a chip would double roughly every 2 years. But experts agree this era is coming to a close, likely within the next 5 to 10 years. For instance, IMEC, a world-leading research hub, predicts that the pace of process node miniaturization will slow down by 2032. This is now the consensus across the industry. So, why is Moore's law hitting a wall? IMEC points to 3 main reasons. 1. Increased leakage current due to the quantum tunneling effect. 2. Physical limits of silicon as a material. 3. Skyrocketing manufacturing costs. The core issue is that when we talk about miniaturization, we can't shrink everything equally. We can't change the size of the atoms that make up matter or the electrons that flow through them. Theoretically, you can't have a wire thinner than a single atom or a current smaller than a single electron. In reality, though, the laws of physics change long before we reach that point. Think of a bucket of water. It pours downward due to gravity. But a tiny droplet might stick to a surface because of surface tension, seemingly defying gravity. In the semiconductor world, when silicon changes the scale, it changes the behavior. Let's look at the first reason, quantum tunneling. At the atomic scale, the laws of classical physics are replaced by quantum mechanics. Here, electrons can essentially ghost through insulating walls that are only a few atoms thick. If electrons leak through a wall meant to stop them, the circuit fails. This creates a hard physical limit. There is a minimum thickness required for insulation, and we simply cannot go thinner. Next, we turn to the limitations of silicon. These are exemplified by a group of phenomena known as short-channel effects, and here I will explain one of the most intuitive examples, drain-induced barrier lowering. Let's think of a MOSFET using a ping-pong analogy. Imagine a ball on the source side, and vacuum devices placed at the gate and the drain. There is a small bump located under the gate. In this setup, even if only the drain tries to pull, the ball cannot get over the bump. But the device is designed so that the ball can cross the bump only when both the gate and the drain are pulling together. This is where problems emerge when the circuit is scaled down too much. Since the ping-pong ball and the bump, standing in for the fixed size of electrons and atoms, cannot shrink, bringing the source and drain too close lets the drain's pull alone lift the ball over the bump, causing the device to malfunction. Engineers have fought this for years by moving to 3D structures, shifting from flat transistors to FinFETs, and now to ribbon FETs, where the gate completely wraps around the channel. But even this has its limits. Finally, there's the cost. Moving from planar FETs to 3D ribbon FETs is like moving from printing on paper to 3D printing. It requires complex, layer-by-layer processing like chemical vapor deposition, which is incredibly expensive. Semiconductor circuits are also fabricated by patterning a wafer with light. In principle, you cannot etch features that are smaller than the wavelength of that light. Therefore, further miniaturization requires using light with a shorter wavelength. However, generating light with even shorter wavelengths requires specialized materials and extremely high energy. Even today's EUV systems incur substantial costs in both equipment and power consumption. If we move to wavelengths shorter than EUV, handling the light becomes even more difficult, and the associated costs would rise to astronomical levels. In the past, continued scaling allowed us to reduce the cost per transistor while simultaneously improving performance. A very sweet situation. However, going forward, it is expected that boosting performance will come with increasing cost, creating a trade-off. So, how do we fight back? First, let's look at what we can still do with silicon. First, we'll push silicon as far as possible. Until around 2030, the era of 1 nanometer node, we'll see an extension of Moore's law through brute force. This involves high-NA EUV machines and backside power delivery to squeeze out every bit of space. Since individual transistors can't get much smaller, the next big step is CFET. This involves stacking N-type and P-type transistors on top of each other instead of side by side. It doubles the density, but the complexity and cost will be enormous. This is likely where silicon hits its absolute limit. As further scaling introduces increasing trade-offs, chiplet-based designs, where each component is fabricated on the process node best suited to it, are likely to become more widespread. For example, both Intel and AMD are moving toward manufacturing logic and cache separately. This trend will likely accelerate, leading to even finer-grained partitioning of circuits. Even companies like Qualcomm and Apple are now seeking specialists who can implement chiplet-based designs using technologies such as Intel's EMIB. What happens when silicon is truly exhausted? There is, to begin with, a line of thinking that says, if you can't change the size of the atom, then change the atom itself. For example, in the CFET approach I mentioned earlier, one promising method is to build up germanium rather than silicon as the semiconductor material when forming the transistor. Further alternative thin-film materials are also being explored, such as transition metal dichalcogenides for use as semiconductors and graphene, which can serve as an interconnect material. As noted earlier, when a material becomes too thin, its surface properties dominate and its characteristics change. However, by using thin film materials that consist essentially only of a surface, this issue can in principle be resolved. That said, even if these material substitutions are eventually realized, they are unlikely to happen in the near term. Another candidate under consideration is analog computing. Although GPUs used for computer graphics and AI currently perform their computations digitally, these applications do not necessarily require exact solutions. In fact, it is generally acceptable to reduce precision, for example, to 8-bit integers, so there is a strong possibility that analog computation would also be sufficient. Proposals have therefore been made to perform NPU or GPU class computations using low-power photonic devices. Until now, the rate at which digital semiconductor performance improved under Moore's law outpaced the rate at which analog computing accuracy could be improved, so such approaches were largely ignored commercially. However, with the slowdown of Moore's law, it is no longer clear how things will play out. In the proposal, optical computing was used. While light offers low propagation loss and high energy efficiency, it is difficult to store, making the design of memory and registers challenging. For this reason, such devices will likely use light only for communication and computation. In the use of photonics, optical interconnects between chiplets will likely be adopted early. The industry is on the verge of introducing glass substrates to improve the flatness of CPU packages, and integrating optical communication paths into these substrates is relatively straightforward. There are also optical logic modules, and developments are underway to integrate encryption functions directly into optical fibers. These technologies may also find use in the future. Quantum computing has long been regarded as a transformative breakthrough. It tackles problems whose computational complexity grows explosively by exploiting quantum superposition to evaluate many states at once, raising concerns that current cryptographic systems could be easily broken once the technology is fully realized. However, only a limited number of algorithms allow results to be measured with few operations, and at present, quantum computers are not considered viable replacements for general-purpose computers. In summary, silicon semiconductors are expected to reach their physical limits of miniaturization in the early 2030s, marking the definitive end of Moore's law. Beyond that point, a variety of technological approaches are being explored, including new materials, analog computing, photonics, and quantum technologies. It is no longer clear whether simply waiting a few years will yield better performance at the same cost as it did during the era of Moore's law. Even so, the progress of computing will continue, albeit in new and evolving forms. Thanks for watching. If you enjoyed this deep dive, don't forget to like and subscribe for more tech breakdowns. See you in the next one.